Hello students, in this video we are going to talk about slew rate. So slew rate is an important property of an amplifier in terms of large signal. Now in this particular video we are going to talk about why slewing is happening and what is the important reason why there is a slewing that happens, and basically what exactly slewing is all about. And later on we'll just try to perform some simple calculations and then we will try to end up this particular video. Now, whenever an op-amp is used in a kind of feedback network, and when the input to the op-amp is so large, then this particular op-amp exhibits a large signal behavior, and that large signal behavior is called as slewing. So when an op-amp gets into this particular mode, that is whenever the op-amp is slewing, then the op-amp basically loses an important property of our linear system. So that happens basically whenever it's get into this slewing mode. Now in order to see what exactly that important property that gets automatically vanishes when the op-amp is basically slewing, we'll just try to understand that through a simple linear system first, and then we'll just put our op-amp into a linear system, and then we'll try to provide a larger input, and so that whenever the input is large enough, then the op-amp would get into this from linear system mode, it enters into slewing mode, and then we'll see what is the origin behind that and what causes this particular slewing and how to reduce the slewing, right? Now, so as I said, let me go with a simple RC network because it's a linear system. So I just take a simple linear system where only passive networks are used, or passive components are used in this, and there won't be any slewing in this particular circuit. Let us assume that the input is specified in terms of Vin and the output is specified as Vo. The output response, the step response, could be written as something like Vo of t, and if I assume that the input is applied with a step whose magnitude of this, or the height of this particular step is given with a value of V0, then I can write V0 times that of the forced response minus the natural response. So this is what we would end up the moment we apply, and I also have to specify this U of t in order to make sure that I apply a step signal at the input, right? Yeah, so out of that, the parameter tau is nothing but the time constant, and whose value is equal to R1, like R times that of C. Okay, let me remove this C here. Now, to know the rate at which the output rises, because the moment I apply a step input, we know that the output takes some amount of time to reach to its final steady state. And if I want to know the rate at which it moves on to its final state, then what we can do is we can just gently try to differentiate this equation. Now when we do this differentiation on this particular expression, we would end up with something like V0 divided by tau, and then e to the power minus t by tau. And there is something that we have to note about this particular expression. So clearly the rate at which this expression or this particular output voltage rises is proportional to this V0. So which means that say for example, if the magnitude of this V0 input has right now doubled, let me use a different color. So what happens to the output then? Okay, so this is right now the new V0 that I have, and what would happen to the output? Now in that case, the rate also has to get doubled, right? Because both are basically proportional to each other. So in short, I can just write it as V differentiation of this quantity is basically proportional to our V0. So if this get doubles, then even the rate at which the output rises also has to get doubled. So which means that I need to get a waveform which looks something like this, correct? So the slope of this will be double the slope of when compared to the previous slope that we had. This was for the previous value, and this is the newest value that I have. And this is an important property, and this is the property that I was mentioning before. Like during slewing, that is whenever the op-amp gets into this slewing mode, the op-amp basically loses this particular important property, which means that the rate at which this rises will not follow this particular expression, and that is what we are going to see right now. So for that, let me try to put my op-amp circuit in a negative feedback. This op-amp right now is assumed to be a linear circuit with a gain of A here, okay? And this op-amp also has some kind of output impedance, and that output impedance is represented by R out here. Now the current through this resistor R out, let me mention with an arrow, could be written as the potential difference between those two nodes, right? So now what I really wanted to know is what is the potential of this node, so that I can write the current through the resistance R out. Now basically if I take this node as my node Vx, then the output of the op-amp would be nothing but it is Vn minus Vx, and this difference is basically magnified by the gain of this particular op-amp, and that is the potential that I would get at this particular node. And what is this Vx and how will I rewrite it? So this Vx is nothing but the drop across the resistance R2 divided by R1 plus R2 times that of V out, and this node is right now is at V naught. Now that I just want to measure this current, and this current value could be written as, okay, let me choose a different color, yeah, is nothing but the potential, which is Vn minus Vx times that of the gain of the op-amp, okay, this node voltage minus this node voltage, which is V out, and the whole thing has to get divided by R out. And this current basically flows out of this particular node, and then it basically finds two paths here. One is across the capacitor CL, the other one is basically across the resistance. And again, what happens is, if I assume that the input input impedance of this op-amp is so infinite, then none of the current would flow in this particular path. So all of the current would generally flow across the resistance R1 and R2. Now rewriting these currents, the currents that are leaving out of this node, could be something like this, right? The first current component is nothing but V out times that of the impedance, okay, which is 1 upon this quantity, so that it comes to the numerator, plus the current that is flowing through this branch, which is nothing but V out divided by R1 plus R2. Now rearranging this entire equation in terms of V out by Vn, we would end up with a kind of expression which would be V out by Vn in terms of S domain could be written as gain divided by 1 plus A R2 by R1 plus R2 plus R out divided by R1 plus R2, and then SCL times that of R out. And this is the expression that we would end up after doing all this rearrangement. I will just try to simplify this expression by assuming something. Like if I assume that the value of R out is so lesser than the value of this R1 plus R2, then what we can do is this quantity or this particular parameter would be much more smaller, right? So I can drop down this particular expression out of this V out by V in transfer function. Now after dropping, we would end up with something like this, right? And now I'm just going to take out some of the parameters out of this equation, as we know that we have already worked on such kind of expressions. Now what I really mean by this R2 divided by R1 plus R2, so what exactly is this particular term? This is nothing but the feedback network, right? So which we can also represent by something known as beta, and let me replace that, where beta represents R2 divided by R1 plus R2 factor, so that I can just plug in terms of beta, so that my equation becomes simple. Yeah. So now we are familiar with this equation, as we have already seen in our previous classes. It's just what I'm going to do is I'm just going to take out this particular expression out of this term and push it to our numerator. And what I really write here as V out by V in of S is nothing but our closed loop gain, which we normally use a small letter, right? Yeah, so this is the closed loop gain, and that could be written as open loop divided by 1 plus A beta, and this quantity signifies our DC parameter, and it has a pole. Since our open loop had a single pole, even the closed loop system ends up having a single pole in the system. So which could be written as something like CL R out divided by this entire term, which is 1 plus A beta over here, right? Now, so let me just pull out some space. Yeah. So now out of this, what is the value of tau that we get out of this equation? That is the closed loop tau. As we know that the tau is basically, it's a product of R and C component, and in this case, when I really map to this equation to the denominator, what I have here is nothing but it is CL R out, but this quantity is being reduced by a factor of A times beta, which means that our bandwidth has got raised by this particular factor, right? Because this is in terms of time, and when I do that in inverse, it goes in terms of frequency, and we have already discussed about this in the class. Yeah, so this is the time constant of our closed loop system, and I just want to write this particular equation in terms of time domain. So which we normally do, we know that this is our DC gain, and if I assume that my input has a magnitude which is equal to V0, then I can write V0, which is basically the input magnitude or the height, and this would be magnified by this gain. There is nothing but the closed loop DC gain, correct? And we normally write the remaining part, that is the forced response minus the natural response, and I have to substitute this U of t. Now clearly, so why did I took all these pains doing all this expression is to show that this expression also depends, like when I try to observe what is the rate at which this output is going to rise, it will also get me the same expression, right? The same type of output that we will get it. What I really mean is, when I do this V out with respect to dt, then this equation is also proportional to our V0. So even here we got the same thing, right? Even this particular expression also has the same form. Now the point here is this equation, like if I could able to follow this equation for any step input or any magnitude of step input or the value of V0, then the circuit functions as a kind of linear system. But in case for a particular value of V0, which could be a larger magnitude, okay, so for this particular V0, if the system couldn't able to produce an output which is rising at a rate of that is proportional to our new value of V0, then the circuit is said to have a slewing property, or the circuit is said to be slewing. Basically, it is not following this particular proportionality over there, correct? So let me explain this phenomena with a simple structure here. Here, each of these waveforms that was mentioned here is basically an exponential signal. That is, we have an output V out of t, okay, and that is basically proportional to the term V0, okay. Now, and along with e to the power minus t divided by tau, and this kind of expression, and which has been plotted for different magnitude of V0. The first one we have got for a smaller magnitude of input. The second one, which is the green one, which we got when we apply this amount of magnitude. So in the similar way, as I keep on increasing the magnitude of the input, what happens is we generally have to have this kind of outputs. Okay, so this is the outputs that I have plotted with respect to a linear system. Clearly, the left hand side indicates all the type of input signal magnitudes that I have applied, and if a system is linear, then it has to follow these kind of outputs, and that is what is being plotted. But say for example, for the magnitude that is somewhere here 1, 2, 3, if I'm not getting such kind of waveform, say for example I get a kind of waveform which looks something like this, okay, the rate is not the same as we had before. I think this color is pretty okay, so let me use a different color. Okay, so what I really mean is this number 1. Okay, so this number 1 is not trying to follow the waveform that is generated here. This waveform is totally different, but the rate at which this is rising is totally different from the rate that it is following. Okay, and then later on, after a while, if the output tries to follow, then the circuit has switched, has come back from the slewing back to the normal action, correct? And again, if I go for this is denoted with the green color, which is number 2. And now what happens is the output doesn't follow this particular waveform, and it follows something like a kind of ramp output, okay? And after a while, it just comes back to this particular output, okay? So in each of the cases, what happens is like the output never follows initially the exponential curve that we have drawn, okay? And later on, it settles down to the exponential response. So in 3 cases, so basically 1, 2, and 3, what happens is the op-amp basically suffers from slewing. Okay, it loses its linear property in these regions. Okay, so somewhere here, right? So for this particular third waveform, it almost loses its linear property till this particular point in time. And in that way, the green one loses its linear property till this particular point in time, right from 0. And the blue one has lost its linear property right from 0 to this particular point in time. So clearly, any input that is greater than this particular 1 magnitude has a kind of a constant slope, right? So this slope is not different for 1, 2, and 3. They are all same. Okay, now whenever an op-amp exhibits such kind of slope, conveys the slew rate of the op-amp. Whenever the op-amp is suffering from slewing, then the rate at which this particular output rises gives us the slew rate of the op-amp. Now to understand why does these outputs 1, 2, so for the inputs 1, 2, 3, why does these outputs are not corresponding to those outputs that's supposed to follow in a linear system? Let us try to understand the origin of this particular slewing. So let me have the circuit, that is the circuit that previously we have drawn, is being replaced with a realistic op-amp circuit here. Okay, and we have maintained the same type of feedback R1 and R2, and then we have the capacitance load CL that is attached here. Now let us assume that I have applied a small step input. Okay, so the magnitude of this one, let us assume that it is equal to del V, the height of this particular step input. I'm talking about a time where if this is my origin of my signal, then any time before this, we assume that this is the condition that I have. Now what happens the moment I apply the signal at time t equal to 0? Now this creates a potential difference between the gate and the source, right? So this del V has to get divided into 2 halves. One half would appear here because I apply differentially, and the other half would appear across the gate and source of our M2. And due to this, what happens is the current basically takes this form, which flows from higher potential, that is from drain to source, and the magnitude of this particular current would be equal to GM1 times that of del V by 2. And since because of this mirror structure that is formed due to M3 and M4, this would be reflected as GM1 del V by 2. Now because of this minus del V by 2 across this VGS of M2 transistor, the current will have the opposite direction, and this current magnitude is given by GM2 del V by 2. And these two currents would actually merge at this particular Vout node, and the magnitude of that one could be written as something like GM1, 2. If I assume that both the GMs are same, then I can write it like this. And now what happens is, it is this current that flows through this capacitance. So again, we are assuming that the resistance R1 and R2 is so large. Now what happens is the current would basically goes to the least impedance path and tries to charge up. Once the voltage across this capacitance keep on rising, what happens to the output node voltage? So this will keep on rising from the previous value, which was assumed to be 0. It keeps rising up, and when this node rises up, obviously the node Vx will also try to rise up, correct? And in a way that it creates an opposite action to the input that is being applied here, and that is why it is called as a negative feedback. So if the circuit follows this kind of current action, then obviously we would end up with a Vout with respect to time could be returned as something like V0, and then the gain that is nothing but our closed loop gain times, and then something like e to the power t by tau CL, correct? Yeah, so basically the output would follow this kind of expression, which means that the circuit still has that linear system property in it. Now let us go for a different case. So let me apply a larger step input, a positive step input to the M1 gate. So this time I'm applying a quite larger step input. Now what happens right now? Now basically when this larger step input is applied, it's obvious that there won't be enough VGS across this M2 transistor, right? And due to which, what is the current that flows in this transistor M1 when the transistor M2 is turned off completely? It would be just equal to ISS, right? So all of the current ISS has to flow through this particular branch. And since because of this mirror structure, the same current has to flow even across this drain of our M4 transistor, which is supposed to be ISS. But since because the bottom transistor is completely off and it cannot accept any current through it, then all of the current, it would actually takes this particular path and tries to charge up the capacitance. Now, what is the rate at which this capacitor would right now get charged up? I guess you get the answer. We know that the capacitance could be returned as dV out by dt is basically given by the current divided by CL, right? Yeah, so this is nothing but the rate at which the output right now increases. Clearly this expression indicates that this rate at which the output doesn't depend on our input magnitude. You see, I have a magnitude of del V here, but this magnitude is so large, and what happened is like when this particular input is so large, it has actually break down our feedback loop across this M2 transistor. By turning off this M2 transistor, we have actually break down our feedback loop in the system. And again, the other fact here is this dV out by dt term is not proportional to our del V term, and that is actually the problem in this case. So which means that I don't have the rate term that is basically proportional to our del V term, which means that our circuit is right now slewing. Okay, now what is the rate at which this is slewing? And that is actually equal to the current, the tail current, divided by the capacitance that we have, and this corresponds to a positive slew rate. Now let us see what happens when we have a negative step input. So it's obvious when we apply a negative step input, then what happens is this transistor M1 will be driven into cutoff region, and all of these transistors would move into cutoff regions, right? So I have M1, M3 and M4 all being in cutoff, and it's only our M2 transistor that is right now that is turned on, and due to which the current ISS, all of the current ISS would actually flow through this path, correct? And that is what will happen. Now how will I measure the rate at which the output is getting degraded? It is again the same thing, like dV out by dt would be equal to minus, because the current is moving out of the V out node, ISS divided by CL, and this corresponds to our negative slew rate. Okay, so again I try to emphasize on the point that right now this rate at which the output is getting slewed doesn't depend on our input del V. Okay, now how long this action would keep on continuing, because I didn't even discuss the same even in the previous case, but the point is like how long this will happen. Let me go over the previous circuit. How long the output would have this kind of relation. What happens is like this is the rate at which the bin of or the voltage across the capacitor keeps on rising, and once it reaches a particular value, what happens to this node? This node will also try to move up, right? So this node will also try to increase when the output voltage across the capacitor keep on increasing. And the moment you create a potential difference between this Vin and this particular node Vx, which is quite enough, right? So when the potential difference is so small, because this node is keep on rising, and it actually makes the difference between this Vin or the M1 gate to the M2 gate very small, and in a way that the transistor M2 will get into saturation region, okay, or which is basically turned on, okay. So the moment this M2 transistor gets turned on, then the rate at which this equation that I have written will not be followed. What would be the rate then? So what would be this rate then? What would be the rate at which the output changes once the M2 come into action? So that would be again proportional to our okay, so I use del V, right? Yeah. So this output rate at which the output changes will be proportional to this one once our transistor M2 come back into action. And the same phenomenon applies even for this particular circuit. So this clearly explains an important observation that we can make, is that the slewing is basically a non-linear phenomena. So this nonlinear phenomena gets into picture just because of the limitation of the current, right? Because the rate at which the output changes is basically defined by the current or the tail current source that we had in our circuit. Okay, if you want to have a higher rate, like in a sense like I have shown a graph, right? Yeah. In other words, I can make sure that this particular slope could be raised up. Okay, that is our slewing slope. I can just write it. Okay, so the way that by which I can shift the slope from the previous slope factor to the new slope factor is by increasing the current, right? Because we know that right now during slewing it follows this expression, correct? So either by reducing the value of CL or by increasing the value of current, I can increase the slope of this, okay, so that it covers up most of the heights of our inputs, correct? Yeah. So if our amplifier is supposed to amplify a sinusoidal input, then and let us assume a particular signal here so that it becomes clear. So let us assume that our amplifier is supposed to amplify a signal whose value is given by sine omega naught of t, okay, and this is the input signal. And so what should be the slew rate of our op amp so that this input signal is amplified without entering into a slew mode? So that I think, like we have already seen in our AMC classes, that value should be equal to V naught times that of omega naught. Okay, so I need to have a slew rate that is equal to V naught times that of omega naught, so that for any signal whose frequency of this magnitude and whose amplitude is of this value can be cleanly been amplified. Okay, so the thing is, like the output would be much more corresponding to our linear circuit. But what if I couldn't able to satisfy this condition, like I have a slew rate of an op amp which is lesser than this requirement, then obviously between the input and the output there will be a slewing. Okay, so which means that if I have a signal of this kind at the input, then the output will have a kind of wave, something like this. Clearly this is not the way of output that we expect, right? So we wanted a kind of sinusoidal output, but clearly whenever the op amp circuit suffers from slewing, then this is what would happen. Okay, so now we'll just focus on one more example before we end the session. So I have drawn the circuit and we just want to compute the small signal step response. So I mentioned here as a small signal step response, and I'm not talking about the large signal. Okay, so we know that whenever we work with small signal, it's obvious that the output would be a kind of or the entire system could be assumed that it is working as a linear system, right? Yeah. So based on that, let me write the question. So Again, this entire circuit we can model in terms of a simple amplifier. Okay, and so what happens is I have my V in here, and then this amplifier has a gain, so that instead of drawing an amplifier, I just model them as a kind of voltage controlled voltage source here, which is gain times that of the input, which I take it as V1. Okay, so plus and minus, and this would be the gain times that of V1 is the potential that I have here. And again, this circuit will have some output impedance, which I labeled that as an R out here. And this entire thing could be treated as a kind of op-amp circuit. Now clearly, I have to take out this particular signal, and then I have to feed it to the other end of our input, right? So this is my Vout node, and across the Vout node, what I have is two capacitors in series. Correct? And I'm taking the output across the capacitor C2, okay, and then feeding it back to the input of our op-amp, and here is our Vout. Okay, so now let me again do the same job here. So I just want to know what is the voltage that I have here. So let me label this node as P, and I can just write, okay, let me directly do it. So the current across this resistance R out could be returned as the potential difference between these two nodes, right? So what is the potential at this point? This is nothing but the gain times that of V1, right? Now what is the value of V1? So V1 could be written as V in minus the node Vx. And what is the node value of this one? It is nothing but, since we have a capacitor, what I would get at the top would be C1 divided by C1 plus C2 times that of Vout. And this is the potential that I have across this V1. And if this is getting multiplied with the gain, then that corresponds to the node potential Vp here. Yeah. So now let us come back to our business, like what would be the current over here. So this current could be written as something like Vp minus Vout, which I have to put in here. Okay, so C1 plus C2 Vout, and then the gain minus the Vout term, and then this current obviously has to flow across these two capacitors, right? So what would be that quantity? And that is equal to Vout times that of C1 C2, because the capacitors are in series, so that we have to write it in terms of parallel combination, right? So I have to write it as C1 into C2 divided by C1 plus C2 times that of the S factor, right? Yeah. So plugging, like doing all arithmetic, we would end up with a kind of form. Let me try to put it here, which is Vout by Vin would end up with something like gain divided by 1 plus C1 divided by C1 plus C2, the gain, and then C1 C2 C1 plus C2 times that of S into R out. Yeah, I think here in this case I forgot to write this term here, that is 1 upon R out. Okay, so again this particular factor could be replaced or could be sensed as something known as beta factor, right? So beta is nothing but C1 divided by C1 plus C2. Okay, and again whatever I've written V naught by Vn of S is basically nothing but the closed loop gain. So this closed loop gain is related to, again, the DC closed loop gain, which could be written as A upon 1 plus beta times that of A divided by the whole factor, that is 1 plus the S factor and the time domain factor. So C1 C2 divided by C1 plus C2 times that of R out, and the whole thing, total time constant, would get divided by this 1 plus A beta factor. Okay, now what we really wanted out of this expression is the CL factor, that is the tau CL factor, which we normally get it by tau is basically is a product of R and C, and we have the C term and then the R term here. So that is our closed loop time constant, and once we get to know this one, then we can really write what is the step response, right? V out of t is nothing but the the step input magnitude, if it is V0, then that has to be multiplied with the DC gain of this quantity. So I can take this result, which is A upon 1 plus beta times that of A, okay, and I need to have a forced minus the natural response, and this is the output that I would get, or the small signal step input. Now let us try to compute the slew rate, because that is the one that is more important, right? So the next question that we have to solve here is to calculate the positive as well as the negative slew rate for the circuit. The magenta color that I have used is all like transistors that are off. So at what condition it will be off? It is when I apply a negative step input, then our transistor M1 would be off, okay, and whole of the current would basically flows through this transistor M2. Now how will we compute the slew rate, and where this current ISS would come from? Basically when this is off, then these transistors would be basically off, right? Yeah. So what is the way by which I would get the current is through these series of capacitors. So it is pretty clear that I would get dV out by dt will be returned as something like minus ISS divided by the capacitance, and that capacitance, since they are in series, the equivalent capacitance value could be written as C1 C2 divided by C1 plus C2, and that is the slew rate. It's obvious. Then what would be the positive slew rate? So in the case of positive slew rate, I have a very large positive step input, and due to which the transistor M2 turns off, and due to which what happens is all of the current has to flow across our transistor M1, and since because of the mirror structure, this will be forced across the drain of our M4, and that would try to charge these two capacitors, and the rate at which this charging would happen initially till our transistor M2 comes back into action would be equal to ISS divided by the combination of these two capacitors, okay, and this is nothing but our positive slew rate. So let us do a final problem on based on the slew rate. So I have given some information, and I wanted you to calculate how long like when a step of 1 volt is applied at the input, how long does the circuit takes for the current ID2, that is this ID2, right? So this value of ID2 to reach 0.1 times that of the ISS value. Now how would we proceed this thing? Like we already know what is the value of tau factor and all those stuff, but the point is like how would we address this particular problem here? Now a simple assumption that I am going to make here is the value of this ID2, since it has been mentioned that is equal to 0.1 times that of ISS, I'm going to assume that during this small amount of current, it is so small that during slewing, I'm going to assume that all of the currents are going to flow across this, and due to this mirror action, the ISS appears here, right? And to make the simplification, or to do this particular problem, I'm going to do a simplification assuming that all of these currents are flowing across these capacitors, and this becomes a negligible quantity just for the computation purpose. Okay. Now what happens is, in that case, the current is charging these two capacitors, and now that I just want to measure what is the voltage across this node Vx. Now what happens is, like previously I would had some voltage before the application of a step input, okay, I would had some voltage before, and after a particular period of time the output would have a kind of response like this, right? And then later on it follows the exponential, and then okay, so here the initial slope, okay, is basically defined by the current that is flowing through these two capacitors. And what was asked was like how long it takes for the current to reach to 0.1, which means that this particular transistor has got turned on, okay, that is, we are talking about the edges where the transistor is completely off, and after a while the transistor makes on. Okay, after a particular period of time, what happens is the M2 gets into action, and then it is turning on, and during turn on condition it tries to draw 0.1 times that of ISS current, correct? And that is what we are trying to do it. During this time, I'm just going to write this Vx. So the rate at which the Vx changes over a period of time, let us assume that this time at which the current drawn through M2 transistor is basically 0.1 times that of ISS. So that particular time, okay. So I will have some potential minus the previous potential. So at this node, or at this particular point in time, what happens is the output will, or this particular node will have a different value, right? Now in this case, I assume that the transistor is totally off. Okay, now what would be the rate at which I move from this value to this value? The answer is, it is pretty clear that at this particular point in time, the rate at which the output switches, or the rate at which this node Vx rises, is basically defined by this quantity, right? dV out by dt, which is nothing but the slew rate, is defined as ISS times that of the capacitance, correct? C1 C2 divided by C1 plus C2. The current that flows, or the voltage that creates this particular rise, is basically defined by the drop across this capacitor C2, right? So ISS, the current that is flowing across the capacitor C2, in order to change this node voltage from the previous value, which was at Vx0 to Vx of t, okay? And so this is basically the dV term, correct? And I need to have the t term, so which is nothing but dt is mentioned as t here, and that when it gets cross multiplied, it moves to the right hand side, right? So this is basically dvx by dt term, and this dt term is nothing but is equal to the time from the origin of 0. Okay, yeah. So now let us see what was the bias condition that we had just before the time t equal to 0. That is, I think you would have learned in your networks, that is at time t equals to 0 minus, I think somewhere here, I guess, right? Yeah. So what was the DC currents that are flowing across this transistor M1 and M2? So basically, the currents that are flowing would be equal to half the value of ISS, right? In both the cases. I forgot to mention what is the ISS value. So this is equal to 1 milliampere. Okay, yeah. So if there is a current flow of 1 milliampere, then half the milliampere will flow across the drain of M1, the remaining half would flow across the drain of our M2 transistor, correct? And this is the condition that we had when before the application of our step input, and I can state it like this. Now let us try to compute what is the amount of VGS value that we had, or the VOV value that we have for this transistor M1 and M2 under this condition, like at time t, that is just before the rise of our input. Okay, so that when we do it, which is nothing but VOV 1 or 2 is one or the same because the currents are same, and that would be given by 2ID divided by Kn dash W by L. And once we plug in all of these values, we would end up with a result. I'm not going to do all those things, but I would write the final result here, which is 1.93 volt. And this is the VOEs that we had across this M1 and M2, or basically the DC conditions at these points. Okay. Now the moment, let us go with to a time period at time t, or time equals to t. Okay. So in this particular time, at time t equals to, or time equals to t, we have right now ID2 that is equal to 0.1 times that of ISS, whereas the remaining current has to flow through ID1, which is equal to 0.9 times that of ISS, right? So this is at this particular time in action. Okay, I have taken the two extremes, and in this particular case, we know that basically the current ID is given by half Kn dash W by L, and then in terms of VOV or VGS minus VT the whole square, right? So this is the condition that we have when the transistor is in saturation region. And since because the transistor both are on and the transistor is basically in saturation in both these conditions, I can just make a simple ratio. Okay, so I'm just going to divide this ID1 divided by ID2, and that would be something like 0.9, because these are the values right now that is held by both these transistors. So I just substitute 0.9 divided by 0.1 times that of ISS. ISS will get cancelled, and that is equated to this quantity. So again, I have common terms for both the transistors, the W by L, K and dash, and the half term. So the end result would be something like VGS1 minus VT the whole square divided by VGS2 minus VT the whole square. And now taking the square root on both the sides, I would end up with VGS1 minus VT and then VGS2 minus VT, that is equal to 3 here. Okay, now let me just write what is the voltage right now that I have across this VGS1 at time t equals to t, and that would be written as something like this into VGS2 with respect to the time t, time equals to t, and keep skipping the word. Okay, so this is what we have it here. So we know this condition, right? Because this is the condition at time t equal to 0, and we know the initial condition we had at time t equals to or time equal to 0. So this quantity is basically whatever I had before plus what is the newest value that I have added to it. That is, I have added plus 1 volt, correct? So to this quantity I need to add plus 1 volt so that I can represent this entire term with this value, correct? So because I applied a step input after time t equal to 0, and it is still there even at time t here, okay, because the output might take some time to rise up, and that is also like with respect to t we are measuring it off. Okay, so I know this quantity pretty sure. Okay, the one thing that I am not sure is this quantity that I have, correct? So what is this value, which is nothing but we had derived before, right? So in the previous condition, so this value is our value that we had at time t equal to 0, or just before the time t equal to 0. So I'm just going to substitute that quantity over here, and to that I just add 1 volt, and that has to be equal to 3 times that of the new value of VGS2 here, because this quantity is not sure, correct? And the end result of this, like after doing all this math, we would end up with VGS2 of t, that is at time t, the rate at which this has been raised up is given by 1.193 divided by 3. We will end up with a value which is equal to 0.397. Yeah. So now what are we going to do with this value right now? Clearly this is the result that we are talking at the beginning, right? Because this quantity, I know what is this quantity is all about. So this quantity is nothing but the voltage at the gate. And what is this quantity? Again, it is the same voltage at the gate of our M2 transistor, but at time equals to t here. Okay, and that is what we have computed right now. So the value that we had at time t equal to 0 is this quantity, and the value that we are getting at time equals to t is the one that we have got right now, and this is the voltage it has raised up. And so when we subtract these two quantities, I will just move on to the next page. Okay, so basically it is VGS2 of t, okay, at time t minus VT minus VGS2 at time t equal to 0 minus VT, Okay, so there is a potential, obviously there is a potential difference between them, and this could be returned as with those values, which is 0.397 and the previous value was 0.193, and we have some voltage difference. And how will I map this one, right? I can cancel out the common terms that we have here. So this is like I have source common and VT common, and here again the same terms. So these terms, when they get cancelled, what actually these differences is giving us is nothing but VG2 at time t equals to t minus VG2 at time equal to 0 here, okay, which is nothing but our Vx of t minus Vx of 0, okay. And this quantity is basically assumed to equal to the slew rate, and that is given by ISS divided by the capacitor C2 and into the time that we have, and this is the time that we are expecting. Like that is the calculation that we wanted to do, how long it took for us to reach from for the ID2 to reach to 0.1 times that of ISS, right? So I know this quantity, substitute all of those values, and we would end up with something like time equals to 102.3 picoseconds, and that is as simple as that. Hope that we have done enough examples, because the theory in textbook is more sufficient, but still I thought let me give a kind of intuition and then try to do some problem. Okay, hope this video is useful. Thank you.